So in this video we're going to look at rates of change. So what do we mean by rates of change? Well, let's think about money. Money can increase at a steady rate like this, or it can fall away. It can diminish at maybe a fast and then a slightly slower rate until finally it disappears altogether. Let me think now of the example of a jar filling up with water. So the level of the water increases at a steady rate. But if I now redraw the jar and think of it going in the opposite direction, then the level falls away rapidly and then rather more slowly as it empties right to the bottom. Now, to see this on a graph, we'd get something looking something like this. So we've got two lines, one of them going upward in the positive direction. In other words, if I think of what direction my numbering goes, then the distance is increasing in this direction, the time is increasing in this direction. So we say this is going in a positive direction, it's a positive angle, so because it's going up, we know we've got the forward direction for our velocity. So distance over time gives us velocity. On the curve, however, we're going in the opposite direction. We're still going forward in time, but the distance is diminishing, so we're going backwards. Also, we can see that instead of going backwards steadily, as we've got with the forward direction of the line, with the curve, we've not got a steady decrease in velocity, we've not got a steady slowing down. What we've got is, first of all, a rapid slowing down, and then it eases off until it decreases very slowly. Okay, so how do we understand rates of change from a distance time graph like this? Well, the sort of question you might get in a test would involve perhaps not necessarily working with a graph, but filling in a table. So a table will sample different points on a line like this, and then you might have to fill in certain values. One thing we might also think about as we're filling in our table is just to have something in mind really to be working on. What about the idea of a train? So we've got a train, or maybe two trains, one of them going from Waverley Station in Edinburgh, let's say, to St Pancras Station in London. And this train is going to go at a steady speed. The train going in the opposite direction from St Pancras to Waverley is going to go not at a steady speed. It's going to go rapidly at the first part of its journey, and then that speed tails off as it comes very slowly back into the station. Okay, so that's one way of thinking about it. Another way of thinking about it, given that we've got meters per second, is if we think about two particles and the vectors on two particles. So here we've got a velocity vector going in a positive direction, and here we've got a velocity vector going in a negative direction. So this represents the straight line on the graph, and this represents the curve on the graph. And you can see at our starting positions here, the second particle is going much faster than the first because its vector is longer. But what happens as we go down this curve here, so we go forward in time, what happens is that we get a slowing down until we get to the point where the two lines cross, which means they're going at exactly the same speed, just in different directions. As we keep going on our curve, then the speed gets less and less, until eventually we're hardly moving at all as we get to this part of the curve. Okay, So now let's fill in our values into a table. So we're just going to sample different points on both of these graphs, and let's call this, I guess, problem A. Let's do that there. And we need to draw now an axis like that. Not an axis, just two lines to fill in our values. Okay, so what have we got? Well, at time s, time in seconds rather, we could call this axis t. So let's call this the t-axis. So at the bottom here, we're going to record time as t. And then our distance, well, we might as well stick to this idea of y. So our distance is going to be recorded as y values. And if we fill in our t values, we've got 1 to 10. Now let's fill in some values for distance. So what have we got that's very easy? Well, the very first thing I want to fill in, I think, is this t equals 9. So t equals 9 when y equals 15 when t equals 9, let's say. So when t equals 9, y equals 15. Okay? And when t equals 10, t equals 6, y equals 10. When t equals 3, y equals 5. And I think that will do to be going on with. All I want to do is get 3 or 4 different values. Let's add it in finally our unit value. So when t equals 1, then y must equal 5 divided by 3. In other words, 5/3 or 1 1/3. Let's call it 1.6 recurring. Okay, so a typical problem will say either complete these values, or if we're looking at rates of change, let's just record down these rates. So what are these rates exactly? Let's see if we can write them down. Well, the first rate that we've got is 1.6, but 1.6 what? 1.6 meters for every second, so per 1 second. We don't need to write the 1, we can just write per second. So that's our first rate. Okay. Our second rate, in other words our speed, is going to be 5 meters for every 3 seconds. Well, that's going to simplify to a unit rate, which is 1.6 meters per second. And 10 meters to every 6 seconds is also 1.6 meters per second, 1.6 recurring meters per second, 1 2/3, and 15 meters for every 9 seconds. Also simplifies to a 5:3 ratio, which then we can translate into a 1.6 meters per second unit rate. Okay, so that's thought about sampling different rates, and on a straight line we can simplify them all. They're all in direct proportion to one another, so these ratios can simplify down to the same rate. And it's this constant rate that we call our rate of change. And the rate of change in this case with a distance time graph is going to be velocity. Okay, so what is the velocity? Well, it's the average of all of the rates on this line. And since they all simplify to 5:3, there's our velocity, or as a unit rate, 1.6 recurring meters per second. Okay, all very straightforward so far. Let's now think about one further thing, which is the gradient of this line. So the gradient of a line can be found by taking 2 points on the line and considering the distance on the y over the distance on the x-axis, in this case the t-axis. So if I take these 2 points here, I've got the rise. So how much does it rise? Well, it rises up. Let's just put some dotted lines on here. So it rises up 5 to get to here. Okay, so that's the rise. Over the run, it runs along 3. So gradient is rise over run, which is 5 over 3. And from that, we can get the formula for our line. Y equals 5/3 of t, our dependent variable. Why have we done that? Because you'll have noticed that 5 over 3 is the same as the velocity. The velocity is also 5 over 3, which we can then do as a division. So 5 divided by 3 gives us 1.6 recurring meters per second. So the gradient, if we know the gradient, then we also know the rate of change, which in this case is the velocity. And that idea can be used not only for this straight line, but also to find the velocity at any point on this curve. Okay, so the gradient gives us the rate of change and tells us that the velocity anywhere on this curve is 1.6 recurring meters per second. Let's now have a go at another problem, problem B we'll call it. Okay, so again we're going to look now at this curve here where we've got a slowing down and we've got a variable rate of change. So if we put in our y and t values and fill in our time, advancing in a positive direction always, time cannot go backwards. So let's fill in now our rates. So the rates that we've got already marked on our curve are when t equals 1, y equals 15. When t equals 3, y equals 5. So this is the crossing point with the first straight line. When t equals 5, y equals 3. And when t equals 10, y equals 1.5. Okay, and again, you might want to fill in the other values. They should all conform to the same pattern, but what we'll find is that these are not directly proportional. In fact, y and t are inversely proportional, so these are inversely proportional ratios. And that gives us a bit of a problem. Okay, let's just check that out to start with. So following the same idea that we did above, if we write down the rates, we should be able to see more clearly that we've got a 15:1 ratio to start with, but then later on in the curve we've got a 5:3 ratio, which is not 15:1. Okay, 15:1 won't simplify to 5:3 and vice versa. Here we've got a 3:5 ratio. So order matters with ratios. So 3:5 again is not the same as 5:3. And finally we've got a 1.5:10 ratio. Okay, to 10 meters per second, 1.5 meters to 10 seconds. And if I think about simplifying this to get rid of the decimal, if I double both sides, then I've got 3:20, which is not at all like 3:5. So this is exactly what we mean when we say if we depart from the straight line, then we're going to find a rate of change, in other words, velocity, that isn't a constant number. In fact, it's a variable. It changes constantly. Okay, so it keeps changing. So if it's a variable, how can we express that mathematically? How can we find what the velocity is for this train, if we like, or this particle going backwards? Well, what we need is a variable expression. And so the way we get that, again, is if we think about the gradient. So what's the gradient for our curve? Well, the gradient for a straight line is very easy. We just take the coefficient of t. But here we've got y equals, well, 15 is our constant, but now that's multiplying by 1 over t. So 1 over t, in other words, 15 over t. So that's the expression, that's the equation for our curve, but it's not something that we can simply take that 15 off and then that becomes the gradient. It's not a constant that we're looking for anyway. Now there is a method that I'm going to show you now, which is very, very simple, and in part 2 we'll understand more why this works. But for the moment we'll just go along with it. So it's called taking the derivative. So taking the derivative of the function means deriving from this function on the right hand side of our equation, deriving from this function an expression for the variable rate of change. So how do we do that? Okay, well, it's pretty straightforward. Step 1, we have to, let's just write derivative. Step 1, what we have to do is change this now to be in terms of, to be in indexical form. In other words, to have an index. So the first thing I'm going to do is, instead of saying 1 over t, I'm going to write this as 15 over t to the minus 1. That's the first step. Okay, next step is to take that minus 1 and multiply by this coefficient. So minus 1 times 15. And by the way, we're going to write our derivative as the differential, so we use d, the differential of the distance over the differential of the time. And again, in part 2, I'll be explaining exactly why we write it in this form. So the differential of y over the differential of t, or we just say dy by dt. Okay, so dy by dt is the gradient, and now we take our minus 1, multiply by the 15 to get minus 15. That's the first step. Very simple. So just take the index, whatever it is, multiply by the coefficient. So minus 15 t, and then the second step is we have to subtract 1 from the index. So minus 1 minus 1. Minus 1 minus another 1 gives us minus 2. And that's it. That's the variable expression for our gradient. And if we've got our gradient, then we've got our velocity. Now, one final thing is I don't like that minus 2 on my index, so I'm simply going to convert that back to 1 over t squared. So I end up with my gradient as minus 15 over t squared, like that. So there we are. Not only is that the gradient, it's also the velocity. So if, for example, we have a part 4, so let's just have a couple of problems just to finish this part of the video. So for part 4, we're going to find the velocity, so find v when t equals, let's keep it simple, when t equals 3. Okay, so at this crossing point here. Well, it looks as though it's rather like the velocity for the straight line curve, so for the particle A, if you like. For particle B, it's simply going in the opposite direction, so it's slowing down, or decelerating, say, slowing down. So, but the figure is going to be roughly like this 5/3. So let's see if we get something like that. Okay, so when t equals 3, v, the velocity, equals this gradient. So minus 15. But this time we substitute, oops, let's write that nicely. We substitute in our value for t. Okay? And t is 3, but we've got to square it, so t squared. So t squared is 3 squared, and 3 squared is 9. So our velocity at t equals 3, so after 3 seconds, is minus, if I simplify this, minus 5 over 3 meters per second. And so it is in fact exactly the negative, if you like, of the velocity that we had for problem A. So minus 5/3, problem A, 5/3. So we could rewrite this. Let's do that now. Let's just erase this. 5 divided by 3, so we've got minus 1.6 recurring meters per second. Okay, let's do one more. 5. What about the velocity when t equals 10? Well, before we do that, let's just go back to our graph. When t equals 3 was here, what would the gradient look like, in fact? Well, we know that the rise over run, we're now not rising, we're going down, we're sinking, if you like, and then we're going along. So again, that's minus 5 over 3, so that will take us down to this 6 here. So here's my gradient going down in this direction here, and intercepting the t-axis at t equals 6. If I draw that back, you can see that what we've got, in fact, is a tangent to the curve at this point here. So I'm going to expect something similar when t equals 10, but much less steep. So you can see if I draw a tangent to this curve, it's going to look more like this. Okay, so very different angle, so therefore a different gradient to the one that we had before, but still going in a downward, so negative direction. So we're expecting something less than 1, so minus 0 point something. Okay, so let's use our formula now to calculate exactly what that is. So when t equals 10, v equals minus 15 over t squared, which is 100. Now, that simplifies very easily. I don't need my calculator. I simply move the decimal point 2 places to the left, or the number 2 places to the right, if you like, giving us minus 0.15 meters per second. So there we are. There's the gradient, and the gradient now, we've just divided the 15 by the 100, or minus 15 by the 100, and we've got a negative gradient, and therefore a negative velocity of minus 0.15 meters per second. Lastly, let's check. So this must be correct, because 5 to 3 is the same as this ratio here, 5 to 3. And here we've got minus 1.6 recurring, so that's because it's a negative velocity, but again it checks with when t equals 3, so at this point on our table, 5 to 3, 5 divided by 3 is minus 1.6 recurring, so that's correct. And here we've got 1.5 divided by 10 when t equals 10, so again our method of using the derivative of the equation of the line has given us the right answer, so we say this is correct. So what we've done is we've moved into what's called differential calculus. And we need to sound a note of caution here. Taking the derivative will only work in the way that we've shown in part 1 of this video if we're dealing with polynomial equations. In other words, y equals x, or y equals 1 over x, or y equals x squared, those sorts of equation. It won't work, for example, with exponential functions, So if you've got an exponential, then you're going to have to take a very different derivative, and that gets very complex. But just for the moment, it's nice to know that this works, and it's interesting to know why it works. Now let's give a very simple explanation without giving a proof, and let's start with what we had in part 1, y equals 5/3 of, well, we had t, and that's simply the equation of the straight line. Now, would it work if I did the same for a straight line? Let's have a look. So if I differentiate y with respect to t, or dy by dt, what would we get? Well, we know it should equal 5/3, but let's just think about, well, t is to the power 1. Okay, so 1 times 5/3 would give us 5/3 again, and t to the power of what? Well, when we take the derivative, we subtract 1, so it'd be 1 minus 1, t to the power of 0. Now, there doesn't seem much point in doing this because we know that the gradient of a straight line is the same all the way along. But what I'm trying to find here by using the same method that I used on the curve is what exactly is this point here? What is the rate of change at this instant on my straight line? Which we haven't done yet, we only found an average. Okay, well, if the instant is, let's say, t equals 3. Okay, so let's change that from x to t. Then if I substitute 3 into this, we've got the gradient is 5/3 of t, which is 3, so times 3, to the power 0. Now, by the laws of indices, anything to the power 0 is 1. So we end up with 5/3 times 1, which is just 5/3. So we've got the same result, and we've shown that this method, taking the derivative, works whether it's a straight line or a curve. Okay, now how does this work? Why does it work? Is a very interesting sort of idea. But why does it work in the first place? Well, it's a combination of geometry and algebra. So let's just look at the geometry for a moment. Here we've got our straight line, and it's very easy to find the gradient of a straight line. Here we've got a circle, and it's very easy to find the tangent on the circle. Now the tangent is going to be the same as the gradient that we've been trying to find, which varies, just like a curve, all the way around the edge and the circumference of the circle. So let's have a look at the circle, and that will give us a hint about how we can use this method to find the gradient or the tangent at any point on a curve. So if we join a line from the center to the circumference, in other words, draw a radius to this point, then it's very easy to find the tangent to the circle. We just take a 90-degree angle, draw that up, and we've got a tangent at this point on our circle. That's easy, but when you've got a curve, then it's very difficult to know what we mean by center. And if we haven't got a center, can we be sure that this tangent we've drawn is accurate, is at the right angle? Well, no, we can't. So if we drew it like this, that might look plausible, or like this. So this was the problem that the originators, the inventors of calculus, struggled with until they solved it, which they solved it geometrically and then algebraically. So here we've got the ideal, let's say, of what we want to find. Here we've got the tangent to the curve, but how do we find it? Well, the method, theoretical method if you like, is if we take a point here and a point here and join those points together like that, we can see where this line cuts the curve, these 2 points here, as we bring the angle closer to the angle that we want to find, those points get closer and closer together until we get very close to the angle that we're trying to find, so close that the points in fact have almost joined together, and joining together exactly what we want to do. So this gives us the idea that if we did join those 2 points together, in other words the difference between those 2 points was negligible or infinitesimally small, then we would have found the tangent to the curve. And that's the basic geometric insight that led eventually to the algebra that we've been using in the video. Now let's have a look at finally a parabolic curve. So say you had a curve that was going in this direction like this, shaped like this. This would give you an equation, y equals, let's say 3x squared. So this is a polynomial. So again, if we want to find the gradient at this point here, we can use this method of taking the derivative. So the derivative of y with respect to x this time is what? Well, again, our method is 2 times 3, which is 6, and 2 minus 1 gives us x to the power 1. Well, x to the power 1 is just x. So we've now found the gradient in terms of a variable, because of course, just as on any curve, the gradient isn't fixed, it varies all the way along the curve. So let's now find at this point here, if we have x equals 3, let's mark it here, let's find what the tangent would be at this point here, and therefore find the rate of change. Okay, by dx, there we go. So to get the derivative of y with respect to x, all we need to do is substitute that 3 into our equation here. So we've now got the gradient equals 6 times 3 equals 18. And that then is going to give us the rate of change. So it's 18 meters per second if meters and seconds are the units. What it means is that we've gone 18 up, so that's the rise, and we've gone along 1. So in fact, here we've got a unit ratio. So this is a method that works for any curve as long as you can find the equation of the curve, and as long as that equation is and that curve is a polynomial. So only use this method if it's a polynomial, but if you know what the equation of the curve is and it is polynomial, then using the derivative idea is a very, very quick way of finding the gradient, which then gives you the rate of change. Okay, so finally we can put this in general terms. Rate of change, we've said, is always with respect to time. So if I've got a curve which is y equals the constant of proportionality times the time, and we don't know what the exponent is, so we'll give that a general letter n, so time to the power n, then we can take the derivative dy, the derivative of y with respect to x, we say the derivative of y with respect to x, and we do it simply by bringing that n down so that we get n now times k, and that multiplies the variable t, and the exponent now, or the index, is now n minus 1.